Hello everyone, welcome to my channel Build with Jaswinder. As part of this video series, we will be building the logic to solve this lead code problem 153, which is find minimum in rotated sorted array. In this, you are given sorted unique elements rotated between 1 to n times. What does this mean? So basically, there was an array 1, 2, 5, 7, 9. If you just rotate the array to right by one position, this 9 wraps around the length and it comes here. So the array becomes like this, which is given to us. And our task is we have to find the minimum element in this array. Say for in this example, the answer would be 1 since 1 is the minimum element here. How we can solve this problem? If you think of the brute force way, okay, we could just iterate from left to right and do a comparison element by element, and whichever is the minimum element, we could store it as our answer. Okay, so I'll just write the pseudocode here. So we'll assume that the minimum element given to us is the first element. Okay, and we will iterate from 1 to n minus 1. I'm writing 1 here because we have already checked the zeroth element, and we will just replace the min element if we find a new element which is less than this min element. Okay, this min is a standard operation which is provided in most of the programming languages. This will just replace if this min element is greater than this numzi, so it will just replace min element with numzi. Okay, then in the end we'll just return this min element. And what will be the time complexity of this problem? If you notice, we are just running one loop from 1 to n minus 1, so the time complexity would be O of n, and the space complexity would be of 1, as I'm not using any extra space here. Okay, now can we do better than this? If you notice, the array given to us is sorted, and we haven't used that property to find the minimum element in this brute force solution. Okay, so can we do better than this? Yes, we can do better than this. So I'll just write a better solution here. Okay, now generally when the array given to us is sorted, we could find the element in log of n operations, because we could just reduce our search space by half each time when we are making a decision. Okay, so I'll just use the same example here just to give you an idea how we can use the normal binary search here also. Okay, so this is the array that is given to us. Okay, if you notice, these are the standard pointers that we use in the binary search. This is start and this is end. Then we go to the middle element, which is this one. What we have to do is we'll just check if this mid element is less than equal to end or not. Okay, so there will be two cases. Either this nums will be less than equal to end, or it would be this nums would be greater than the mid element. Okay, these will be the two cases given to us. Can there be a third case? No, it can't. Either this element has to be less than this element has to be I made a mistake. Let me just correct it. So either this element has to be less than this 7, or this element has to be greater than 7. There are only two cases. Okay, now we have to think of reducing the search space by using this information. Okay, i'll just I'll just write down the basic binary search. Okay, so then you will follow up then what I'm trying to say. So this is the simple binary search that I'm about to write. If you notice, it's just simple. Okay, I'll just write the basic binary search. If you find it difficult, then you might check some basic binary search algorithms online, okay, then you will get an idea. Here, what we're gonna do is we'll check the mid element, and the mid element is generally calculated using this approach just to get rid of overflow, okay. And now, if as I said, there could be only two cases, okay. Either this nums mid would be less than nums end, okay, or there will be the other case when this will be greater than, okay. Here I am writing both the cases, okay. So let me show you. So what happens, just think of now, this is the standard binary search that I have written, okay. I'll just create another variable here, okay, which is the min element, which is my answer. I'll just erase this one so that you don't have, so that it don't get confusing. So initially this will be infinity, which is the maximum element, okay. So now when my nums mid is less than nums end, what happened here? When my middle element is this and the end element is this, can I assume that this mid can be the minimum element? Because mid is already less than end. So can I say that my min element can be the, this nums mid could be the min element? I'll just do a check. If it is, then I'll just replace it with the min element. Now, I already know this, that this 2 is less than equal to 7, right? So now where do you think the min element would be? This is increasing. So it has to, the min element has to be in this area here, right? So can I reduce my search space and say that end is equal to mid minus 1? Can I say that? Because I already know that this array here, this array given to me here, this is in increasing order, right? And I have already checked that this could be the minimum element, and now I can reduce my search space from this all the way to this, right? Now what happens in the second case? When this mid element is greater than 7, I'll have to reduce my search space, right, again. But I'll just give you another example so that you can think of what should be, what should we do here. So let's say this is given to us, this is another array, okay. In that case, this would be start, this would be end, and this will be the mid element, okay. Now if you check here, okay, this mid element is greater than end, which is our this case here, right? What should we do here? If this mid element is greater than the end, then can we assume that the smaller element has to be in this search space, right? Because this is sorted and this is rotated. If this is rotated and this is greater than this, then it means the mid element will be somewhere over here. So it means from here, this search space, we could just reduce our search space to this size. So basically what I'm trying to say is, in that case, our start will become mid plus 1. And what in the end, what we're gonna do is we'll just return the minimum element. Okay. So the important step is to realize and to come at this condition. You just have to assume that there will be only two cases. Either my middle element will be less than equal to the end element, or the other way, the mid element has to be greater than end element. If you just formulate this condition, right, then you know that this element, if this element is less than equal to this element, then I can say that this can be the potential min element, right? So I'm just checking here if this could be the minimum element. And if I know that this is less than equal to this, so it means I could just reduce my search space from this to this, right? If you look at this closely, what will be the time complexity of this solution? I'm reducing my search space by half every time. So the time complexity is of log n and the space complexity is of 1 as I'm not using any extra space. Okay. Now I'll just show you the same problem on Leetcode and then we could just use the same logic that I'm using here. Okay. I hope my screen is visible. Yeah. So here if you notice, I'm at the same problem. I'll just initialize two variables here. This is my search space initially. If you remember, I'll store one min element. Initially, it will be the max value that I can have. Now I'll just write the standard binary search solution. Okay. Here it will be a mid element, which I'll calculate in by using this way. This is done to avoid integer overflow, right? So if you remember what I said you earlier, there could be only two cases. Either this num would be less than equal to end, or it could be greater than. Okay. If it's less than equal to end, then I can assume that this element, which is at mid index, could be my min element. Okay. I'll just do a quick check here. If it could be a min element, then it will just get replaced. Okay. Now I can assume that my search space and the middle element will not be in this search space. So I'll just reduce my search space here. So end will become mid minus 1. And the other case, I'll just have to reduce my search space to the right. And in the end, I'll just return my middle min element. So I'll just submit the code and hopefully it should pass. The basic test cases are running. So yeah, so this code passed and the time complexity is of log n as we are reducing our search space by half every time. If you like the solution, please follow and subscribe to my channel. I'll be posting more such videos